A nice problem to think through in all three coordinate systems is if we have a hemispherical tank and it's filled partway up with water to a height h, how much water is in the tank? The natural coordinate system for this one is cylindrical or spherical, but we'll actually also do it in Cartesian. So actually, let's start with cylindrical. And a useful way to think in cylindrical is to think in the ZR plane and look at what a cross-section of the shape looks like in that plane. Because especially in this case where we have radial symmetry, all we need to do is describe this cross-section, and then we can spin it through 2 pi radians. There are two orders in which we could approach this cross-section. We could think of this cross-section as radii going from 0 out to this spherical tank radius, and then heights going from 0 up to h. Or we could think about it in terms of heights going from 0 up to first h, and then 0 up to the spherical piece over some radius. And so clearly thinking about it in terms of height results in needing two integrals. Potentially we can do this in one integral if we just go from 0 out to some radius. What is the radius? We need to write the function of the outer boundary, which was x squared plus y squared plus z squared. Let's say the radius of the tank is a, equals a squared. So this is r squared plus z squared equals a squared. And so that's r is the square root of a squared minus z squared, since r is positive. Now that we understand this cross-section shape, we're ready to set up the integral. It's from 0 to 2 pi in theta. It is from 0 to h in z, and it is from 0 to the square root of a squared minus z squared in r. As I write that, I realize I'm not going to enjoy that integral very much, and that's because there's a z squared in the square root, but there's not going to be anything helpful to help get rid of that z squared, and so actually I want to reconsider my choice of order. First, let me complete this integral. This integral is r dr dz d theta, where this is the volume element in cylindrical coordinates. So actually, I'm going to reconsider. I don't want a square root of a constant minus z squared, and so I'm going to try it as a sum of two integrals, one where z is going from 0 to h over this inner region. This is the region where z is going from 0 to h, and then one where z is going from 0 up to this spherical boundary, and the spherical boundary in spherical coordinates will be in cylindrical, but in terms of z will be z equals x squared minus r squared. Okay, so now it's going to be two pieces. One is the integral from 0 to 2 pi, and I'm going to do this piece first. So, oh no, I need to figure out what this radius is, where my r bounds are ending, and this radius occurs when my height, z equals h, intersects my sphere, r squared plus z squared equals equals a squared. And so I can plug in that h, and I get r squared equals a squared minus h squared. So if I'm thinking about this box, I'm going from 0 to the square root of a squared minus h squared. And then z on that box is just going from 0 to h, r dz dr d theta. And then plus this other part. And there, it's still 0 to 2 pi in theta. And now r is going from the square root of a squared minus h squared out to a. And z is going from 0 up to the square root of a squared minus r squared. And so this is r dz dr d theta. I don't mind seeing a square root of a constant minus r squared at all, because I know that I have the r as part of the volume element, and so this will integrate quite easily via a u substitution. Something worthwhile to note about these integrals is here all the bounds for the cylindrical part are constant, and actually these integrals factor and can just be thought of as a product of each other, because this r doesn't matter to the z integral, it just pulls out. And this quantity is just going to be a number, so I can also pull it out of the integral. And then I'll have an integral in terms of r. That'll be this part. And again, theta's not appearing in that, and so by the time we're done with that integral, it's just going to be a constant. It can also pull out. And so we can actually rewrite this first integral because of these constant bounds, and because the function is not at all complex, the function of integration, we can rewrite it as a product of three integrals. So it's the integral from 0 to 2 pi d theta, times an integral from 0 to the square root of a squared minus h squared r dr, times an integral from 0 to h dz. That's quite nice. And as we go down to the other integral, we might want to ask the same question, but you'll notice that actually the z bounds depend on r, and so by the time we finish integrating in z, we're still going to have a function of r, so we're not going to be able to pull this dz integral out of the integral. However, perhaps you can see by the time we're done integrating in r and z, the r's will be gone, the z's will be gone, and everything will just be a number. And so we can pull this out of the theta integral and be left with the integral from 0 to 2 pi d theta times an integral that's truly coupled, square root of a squared minus h squared to a, 0 to the square root of a squared minus r squared, r dz dr. Okay, so this is ultimately what we get when we set up to find the volume in cylindrical. Now let's set up to find the volume in spherical. In spherical, it's still helpful to look at this cross section that's getting spun through 2 pi. But now we're trying to describe this cross section using bounds of rho and of phi. And if we draw rho going outward, we can see that over this entire area, the outer bound of rho is just a, but over this region, the outer bound of rho is given by z equals h. And when z equals h, we have rho cosine phi equals h. So the outer bound of that upper area is given by rho equals h over cosine phi. Because rho has two different bounds, over here it would go out to a, and over here it would go up to h over cosine phi, we're going to need to split this into two separate integrals. And the place where they get split is this point of transition between them. But now the thing that we care about is not the coordinate of that point, but actually the angle phi naught that occurs when we're at that transition. I'm not going to find that angle phi naught yet. I'm just going to call it phi naught as we set up the integrals. And so the first integral we'll set up is just a piece of a sphere, and so that's going to be very natural in spherical. As I mentioned, theta is going from 0 to 2 pi, and phi is clearly going from phi naught up to pi over 2. Phi naught to pi over 2. And then the radius is just going from 0 out to a. And then we need our spherical volume element, which is rho squared sine phi. And our order is d rho, d phi, d theta. And then we need to add on this other piece, which is a cone, if we spin it around. And on that piece, again, we're going from 0 to 2 pi in theta. And now we're going from 0 to phi naught. So we start at vertical and go down to phi naught. And then rho is quite interesting here because rho is going from 0 out to that plane. And that plane where z was equal to h is h over cosine phi. And again, rho squared sine phi, d rho, d phi, d theta. Okay, and as we look at these integrals, that same observation that we had in cylindrical is happening up here. There's constants in the bounds of integration. The function, the integrand that came from the volume element is quite simple. And this sine phi can certainly get pulled out of the rho integral because it's constant relative to that integral. And we're left with an integral in terms of rho that is going to result in just a number. So we can pull that out. And then in addition, our phi integral, both of these, this is a number, this is a number. Our phi integral is also going to result in a number. And so again, we get a product of three integrals for that upper one. So we have an integral from 0 to 2 pi d theta. an integral from phi naught to pi over 2 sine phi d phi, and an integral from 0 to a rho squared d rho. Okay. Then for the bottom integral, we're in this case where phi is in one of the bounds, and so certainly even though once we integrate with rho, there's still going to be a phi coming in from those bounds. It's not just going to be a number. And so these two integrals, the rho integral and the phi integral, are inextricably linked, but actually by the time we're done doing both of them, we are just going to have a number, and so we can factor out the theta integral, 0 to 2 pi d theta times these integrals that are linked together, 0 to phi naught, 0 to h over cosine phi, rho squared sine phi d rho d phi. Here are the setups in cylindrical and in spherical. In cylindrical, this was the sum of a cylindrical region plus a spherical shell piece. In spherical, this was the sum of a cone and a wedge out of a sphere. And as we look to this first integral, the one where everything factored, this is going to be the volume of the cylindrical piece, and that should be quite clear. We're going to get the d theta gives us a 2 pi. The dz gives us an h. And if we think about what we expect the volume of the cylinder to be, it should be h times the area of the base, where the area of the base is pi radius squared. And so there's going to be a 1/2 radius squared that's going to cancel that 2 and give us the radius squared. And that's going to be 1/2 a squared minus h squared. So the volume that comes from this integral that factored is exactly what we expect for the volume of a cylinder, and the work in this problem will go into finding the volume of the other piece via integration. But actually, I think the spherical integral is the more interesting one to do as an example, and so let's focus on that.